Yeah. Rahman Rahim. I am Ihab Bahrawi, second year mechatronics engineering student, and my partner is fakhri Nabi, third year mechatronics engineering student. We are studying at Al National University. Our today's presentation is about steam power plants and gas turbine power plants. This presentation, in this presentation, we are going to compare between them, and our comparison is based on the course principles of thermal fluids and heat transfer. And our presentation is not going to be detailed due to time limit. So let's get started. First of all, we have to talk about to introduce our presentation in general. Power plants are stations to produce electricity. There are many types of these plants. We are going to focus on steam power plants and gas power plants, talking in brief about how they work and explain how they are controlled by the sciences of fluid mechanics, thermodynamics, and heat transfer.
A coal power plant depends on a heat to turn water into steam. The steam is then sent through a turbine, which generates movement of generator, which in turn generates electricity. Gas power plants are similar to steam stations, but instead of steam turbines, here we use gas turbines.
In this figure, as you can see, we are presenting a steam power plant with all its sections. Steam power plant consists of a single boiler or group of boilers which heat the water and turn it into high pressure, high temperature steam, which moves by piping system to a three-step turbine, which produce a shaft work, a transfer to an AC generator.
Steam leaves the turbine with lower pressure, lower temperature, moves to the condenser, which turns this steam into lower pressure, lower temperature water. This water moves to a pump in a piping system to push it to the boiler as a high pressure water, and the process repeats.
Now we are going to talk about gas power plants. In the gas turbine power plants, air is compressed in a compressor. The compressed air then passes through a combustion chamber where the temperature of the compressed air rises. In the combustion chamber, the air is mixed with a fuel, and there the fuel ignites, and the high temperature and high pressure air is passed through a gas turbine.
In turbine, the compressed air is suddenly expended, hence it gains kinetic energy, and because of this kinetic energy, the air can do mechanical work for rotating the turbine. In a gas turbine power plant, the shaft of turbine, alternator, and air compressor are common. The mechanical energy created in the turbine is partly utilized to compress the air.
Now, let's start talking about work, energy, and efficiency analysis. First of all, we have to start talking about steam power plants. But first, we have to define entropy, which is the loss of energy available to do work. It's another form of second law of thermodynamics. States that the total entropy of a system either increases or remains constant. It never decreases. Entropy is zero in a reversible process, and it increases in an irreversible reversible process. Uh, we are going to talk about ideal Rankine cycle, which does not involve any internal irreversibilities and consists of the following four processes: from 1 to 2 isentropic compression in the pump, and from 2 to 3 isobaric heat addition in the boiler, from 3 to 4 isentropic expansion in the turbine, from 4 to 1 isobaric heat rejection in the condenser. And I have to explain something, which is isentropic means that entropy is constant, and isobaric means constant pressure during the process.
Area under the process curve on TS diagram represents the heat transfer for internally reversible processes. Area under the process curve 2 to 3, heat transfer to the water in the boiler. Area under the process curve 4 to 1, heat rejected in the condenser. Difference between these two is the net work produced during the cycle. Boiler and the condenser don't involve any work, and the pump and the turbine are assumed to the isentropic.
Equation 1 represents that the net energy transfer to the unit mass of a fluid as heat during the cycle must equal the net energy transferred as work from the fluid. Here is the equation. The summation of Q net cycle is equal to summation of Q of the net work in the cycle. Delta Q is equal to work of turbine minus work of pump.
Where
The second
Q1 is
equation, sorry, Fakhri. The second equation talks about the efficiency of this cycle.
where Q1 is the heat transfer to the working fluid. Q2 is the heat transferred from the working fluid. WT is the work transferred from the working fluid. WP is the work transferred to the work fluid. And equation 2 represents efficiency of the vapor power cycle.
Now we are going to apply the steady flow energy equation to the boiler, turbine, condenser, and pump. And applying this equation, we obtain these relations. For the boiler as a control volume, Qn is equal to H3 minus H2. For the turbine as a control volume, work of turbine, the output work of turbine equals to H3 minus H1, where Q equals to 0.
For feed pump as control volume, work pump in equal H2 minus H1, or work pump in equal V multiplied P2 minus P1, and Q equal 0. For condenser as control volume, Q out equal H2 minus H1, and work equal 0.
In this slide, we are going to talk about thermal efficiency of the Rankine cycle, which is, as we mentioned before, the thermal efficiency equals to net work over Qn, or 1 minus Q out over Qn, where net work is equal to Q input ناقص Q على output, and equals to work of turbine ناقص work of pump. Now we are going to present the overall efficiency of the plant. The equation here is the efficiency, the electrical efficiency, where BOE is the power, the electrical power, NOE is the electrical efficiency, MF is the mass flow rate of the fuel, and QF is the lower heating value of the fuel. This equation represents the overall efficiency, the overall mechanical efficiency. BOM is the mechanical power output, and MF, QF are the same as in the equation number 1.
This figure shows the 3 stations and how energy transfers between them. The compressor compresses air which is moved by a system of piping to the combustor. There is mixes with a fuel which ignites, causing the compressed gas to have much more energy and gives it higher pressure. The gas then moves to the turbine which rotates, and the rotating shaft produces output work. There are 2 types of gas turbine power plants.
The first one is the open cycle, and the other one is the closed cycle. And let's now talk about the ideal cycle that the working fluid undergoes. Is the ideal cycle that the working fluid undergoes is in the closed loop in the Brayton cycle. So this is the Brayton cycle TS diagram, and this is the BV diagram. We are talking about all the time talking about TS diagrams because it is new to us, and the BV diagram is discussed already in the course. This diagram is made up of 4 internally reversible processes. From 1 to 2, isentropic compression, there's no change in entropy. From 2 to 3, constant pressure heat addition. From 3 to 4, isentropic expansion from 4 to 1, constant pressure, heat rejection.
Here the heat exchanger is added and the steam undergoes four processes which are process 1 to 2. The air is compressed isentropically from lower pressure P1 to the upper pressure P2. Temperature rising from T1 to T2. Process 2 to 3. Heat flows into the system increasing its volume V2 to V3 and temperature T2 to T3. Pressure remains constant at P2. Heat received equal mCp multiply T3 minus T2. Process 3 to 4, the air is expanded isentropically from P2 to P1 and temperature T3 to T4. No heat flow occurs. Process 4 to 5, heat is rejected from the system as volume decreases from V4 to V1 and temperature from T4 to T1. The pressure remains constant P1. Heat rejected equal mCp multiply T4 minus T1.
Thermal efficiency of open cycle gas turbine plant. Now we are going to talk about three methods to improve thermal efficiency, which are intercooling, reheating, and regeneration. In this presentation, we are going to talk only about intercooling. A compressor utilizes the major percentage of power developed by the gas turbine. The work required by the compressor can be reduced by compressing the air into two stages and incorporation the intercooler between these two stages. Now let's analyze the TS diagram. From the process from 1 to 2 prime represents compression. From 2 prime to 3 represents intercooling. And from 3 to 4 prime represents compression. From 4 to 4 prime to 4 to 5, it's heating in the combustion chamber. From 5 to 6 prime, it is expansion in the turbine.
Comparison advantages. Gas power plant, much simpler than the steam turbine power plant. 2. The size of gas turbine power plant is smaller and has less components. The constant loss is quite smaller in gas turbine power plant. A gas turbine power plant can more instantly be started.
And now let's talk about the advantages of a steam power plant. First of all, it's economical for low initial cost other than any generating plant. Second of all, thermal power plant can be installed in any location where transportation and bulk of water are available. Third, the efficiency is higher than the gas power plant. And last, since coal is the main fuel and its cost is quite cheap than petrol, diesel, so it's cheaper than petrol and diesel, so generation cost is economical.
Comparison disadvantage. Gas power plant overall efficiency is low since 2/3 of the total power output is used for driving the compressor. 2. Problem of starting. Compressor need to be operating those external source of power if necessary. 3. Temperature of combustion chamber is too high, those resulting in a lower life.
For steam power plants, the first disadvantage, the heated water that comes from thermal power plant has an adverse effect on the aquatic lives in the water and disturbs the ecology. Second, large amount of smoke causes air pollution. Third, coal type thermal power plants requires comparatively large duration before it supplies generated power to the grid because of the heating process and etc. And last, low overall efficiency.
problem and solution. Increasing average temperature of heat supply in steam turbine plant by mixing steam after overheats with the product of combustion of natural gas and the oxygen. Development of this idea consists in maintaining steam temperature on the major part of expansion in the turbine at level close to initial temperature.
Increasing efficiency of gas turbine plant by way of regenerative heating of the air by gas after its expansion in high pressure turbine and before expansion in a low pressure turbine. Before before we finish our presentation, we have to present our conclusion. And power plants are a huge application. There is a great tracing in the field of improving these stations. There is a huge energy loss, and if we could save these losses, the efficiency will increase. Power plants could be developed by adding a better smooth piping systems, choosing the best material for the turbine blades, finding methods to increase boilers heat with the lowest costs. In our opinion, if we could improve system that could keep the high temperature and high pressure during the whole process, this is going to make a huge jump in the efficiency and a great step in the world of power plants and the energy production. Our researches about this topic will not stop here, and we have to say a big thank. We have to present a big thank for our instructor, Dr. Ihab Al-surakji. Thank you.